Okay, great. Thank you, Ed, so much for that presentation. We do have some questions that are coming in from our attendees. We are going to move into the live Q&A session right now. So now, Ed, I'm going to read out the first question we have here today. Is there a specific sensor characterization checklist of the attributes you'd recommend engineers to follow before moving on to later stages of integration?
Well, that's a great question. Thank you. So what I would recommend when beginning a sensor characterization would be, if you're using our sensor characterization kit, you're going to find it comes with 3 different analog circuit modules. Each analog circuit module is a different analog circuit. One of them is a non-inverting op-amp configuration, the other an inverting op-amp configuration, and finally a voltage divider. What I would first recommend is taking your sensor and characterizing it using the automated loading profile for linearity on the characterization fixture. It's a 5-step linearity test. It's fairly quick to run the profile, and what you'll see is the voltage versus force curve for that sensor under the selected circuit. Once you run the linearity profile for the 3 circuits that are included with the characterization kit, what you could do is compare the outputs and essentially determine the sensor response that works best for you given the considerations of your anticipated application. Now, once you've gone ahead and got an idea which circuit is going to be best for you, the next step would be to run the other pre-programmed loading profiles, which are linearity, hysteresis, drift, and repeatability. What that will do is give you as we said in the presentation, a performance baseline of the sensor relative to some of its key parameters in terms of those sensor properties. Then once you've gone ahead and characterized the chosen circuit with the different loading profiles, I would recommend inserting the material interfaces that you're considering to be in contact with the sensor. What this will allow you to do is compare the sensor output just by itself and with the chosen loading interface materials. This will give you an idea what your loading interface materials do to your sensor response, and using the onboard adjustable reference voltage or swapping out the resistor and capacitor values, you can optimize the voltage and component values for the interface material that you're going to go ahead and start proving concept with and prototyping with. So that would be the checklist that I would recommend for sensor characterization.
Okay, great, Ed. Thank you so much. The next question here. I'm considering a custom sensor for my device. Can you tell me about the sensor customization process?
Absolutely. The sensor customization process is it's pretty collaborative with Tekscan, both our sales engineering side and our applications engineering side. Generally, the process will involve an engagement with our sales engineering team. What they'll do is they'll work with you to quantify the application, to understand your needs of the sensor, the technology, and then they'll bring in an applications engineer such as myself, to work with you and understand the technical needs of the application. Once we have an understanding of the technical needs of the application, we can determine the type of pressure-sensitive ink that's ideal for the application. We can determine the type of substrate that's ideal for the application, depending on the temperature, the force range of the application, and other application parameters. Once we've understood the technical needs of the application, we can work with what we'll do is we'll take your desired sensor design itself in terms of geometry, shape, size, sensor termination, and we'll work with our mechanical design team to incorporate that into our manufacturing process. Then we'll collaborate back and forth with you on the given design that you're considering, ensure that it's optimal. Then there'll be a prototype phase for the custom sensor where you'll get some samples, you'll get some prototypes, You'll determine that, yes, these are optimal for the application, or no, something needs to be tweaked. And then after that collaboration, we'd move on to a final production of the custom sensor. So in terms of what we'll be looking at during the sensor customization phase, anything from size of the sensor, overall shape or geometry, the electrical termination, the force sensing range, the operating temperature. These are all examples of elements of the sensor that can be customized to your specific application.
Okay, great. Thank you, Ed. Just a reminder to all of our attendees, if you would like to ask a question, go ahead and place it in the Q&A window and then click Submit. All right, Ed, next question. What is the force range of FlexiForce sensors? What is the max load one can withstand?
That's a great question. Tekscan manufactures and designs sensors to maintain their linearity through a wide gamut of force ranges. When we're talking about the absolute maximum that a FlexiForce sensor can withstand before plastic deformation occurs, you're talking about somewhere in the 10,000 psi pressure range. We like to give that number in terms of contact pressure because, of course, the contact area could be variable from application to application. So the 10,000 psi mark is where we could start to see some permanent and plastic deformation in the sensor itself. Now, below the 10,000 psi area, going back to applicable forces, you'll see if you're looking on our online store or at our product catalogs, you'll see sensors with force ranges designated at 1 pound, 25 pounds, and 100 pounds, respectively, for some of the different sensor models. Now, when you're looking at these forces, I would recommend considering the force designation for that sensor that you're looking at as a nominal force range. So, for example, the 1 pound sensor, I would consider that 1 pound to be a nominal force range because by using either adjustable reference voltage or adjustable gain, you can take a 1 pound sensor and easily measure up to 10 to 20 pounds with it by changing the reference voltage or gain of your circuit. Similarly, if you take one of our 100 pound sensors, you could get that sensor to operate in the thousands of pounds by altering reference voltage or feedback resistance or the circuit gain itself. So there's quite a bit of flexibility in terms of the force range you can get out of one sensor. The characteristics that you want to consider when choosing what's best for you is the measurement resolution you're going to be looking for, the linearity that you're going to be looking for, and of course our applications team is always available to help select a force range that's optimal for your application.
Okay, great. Thank you so much, Ed. Just a reminder to the attendees, if we don't get to your question, we will reach out to you following the webinar. Okay, Ed, next question. Why are you applying a square waveform into your reference voltage to your sensor?
That's a great question. So it doesn't have to be a square wave. It can be a DC voltage or a constant voltage. So generally, the sensors are a semiconductive material, and under higher voltages, and when I say higher voltages, I'm talking in terms of something above 1 to 1.5 volts. Higher than that, you can start to affect the sensor's lifespan with higher voltages. Now, if you're going to be living in the neighborhood of that 1.5 volt reference voltage area, we've seen sensors last upwards of 3 million and even more actuations without showing any signs of degradation or loss in sensitivity. So a DC voltage is fine if you're going to be able to power the sensor or supply a reference voltage to the sensor on that 1.5 volt order. Now let's say for your given application, you need to power the sensor with a higher voltage, and a reason for that might be, for example, you need more sensitivity out of the sensor or more of a measurement resolution. So if you want to go higher, to 2, 3, even 5 volts, the recommendation is to use a square wave there so that the sensor has more off time during the measurement. This will help preserve the sensor life and still get the maximum possible sensor life out of the product. We've seen sensors that are being powered with a 5-volt square wave last up to 1 to 3 million actuations easily without showing any degradation by supplying this square wave to the sensor at the 5-volt mark, and then essentially it allows you to get that added resolution without having to sacrifice sensor life. So the need and the what should guide you towards whether you're using a square wave or a DC wave or a DC signal would be what type of measurement resolution do you need? What sensitivity do you need? Can you make the lower voltages work for you? Signal to noise ratio, things like that. And then if you do need the square wave, you could work with our applications team to determine, based on your loading profile and the necessities of the application to determine optimum frequency for the square wave and the parameters of the supplied square wave itself.
Okay, thank you, Ed. This next question is in reference to the proof of concept phase 2. How can I test the A101, which doesn't work on that prototyping kit?
That's an excellent question, and you're absolutely right. The A101 currently doesn't work with the prototyping kit. Just as an aside, we are working to create something that allows easy interface with an A101-like sensor to the prototyping kit and the characterization kit. So stay tuned to our email blasts in our store for more information on that in the near future. In the meantime, what you can do if you're testing the A101 and you want to use the prototyping kit, the reason it doesn't work is because it had the termination for the A101 is solder tabs instead of the standard square male pins that we use on the rest of our standard product line. So, and the reason we do that is to make it easier to interface the A101, our smallest standard sensor, with a PCB via soldering it. Now, what you can do if you're using it with the prototyping kit for now is if you solder a couple of breadboard wires, jumper wires, to the solder tabs of the A101, you can actually plug those breadboard jumper wires into the terminal of the prototyping kit. So that will allow you to still be using the A101 with the prototyping kit. If you need more length, you can solder a couple of short jumper wires to the A101, and then you can plug those jumper wires into the FlexiForce extension cable, which is available through our website or contacting our sales department, and that will give you a much longer length without having to use a very long breadboard wire, and allow you to use the A101 with the prototyping kit. So that's what I would recommend for interfacing the A101 with the prototyping kit at this time. But like I said, stay tuned to our email blasts and our store for more solutions for interfacing an A101-like sensor to the prototyping kit.
Okay, thank you, Ed. Next question. Do you have a sensor which can handle estimated body weight up to 100 kilograms? Do you have a printed circuit board or a file that we can get PCB for your recommended circuit without any add-ons you have in your dev toolkits?
So that's an excellent question, and thank you for that. The short answer to the first part of that question, do we have a sensor that can handle estimated body weight up to 100 kilograms? That answer is yes. We have some standard sensors that can handle force that high. We can also work on a customized sensor solution to handle forces at that magnitude. As far as the second part of that question, do we have a printed circuit board or a file that we can that you can get our recommended PCB without any add-ons in the dev toolkits? Currently, they are not available in the there are circuit diagrams that are certainly available in the documentation of the dev toolkits, and those circuit diagrams will show you the mode of operation of the circuit, so that you can, if you either want to build your own or transpose it to your final design, you can do that. And then we can also work with you if you contact our applications team to lay out a PCB similar to our recommended circuit. There's going to be some resources available at the end of this presentation that show some of our recommended circuits and the diagrams of them. If you have any more further questions on the PCB layouts themselves, feel free to reach out to me directly or our applications engineering team, and we'd be glad to work with you on a one-on-one basis.
Okay, Ed, thank you so much. Just a reminder for the attendees, if you have a question, go ahead and place it in the Q&A window and click submit. Ed, the next person asks, you need to adjust only the first time that you use this sensor, or do you need to apply this characterization every time that you need to use it?
So that's an excellent question. For a given sensor series or a given ink sensitivity, for example, the 1 pound sensors, the 25 pound sensors, or the 100 pound sensors, what you're going to see is the characterization curves for those sensors in terms of the shape of the curves, given your material interfaces, given the components that you select specific to your application, the trends and the overall shape and behavior of the characteristics, will be constant. You'll see some variation in absolute values that are being output, but the overall trend, behavior, and shape of your output characteristics, will remain constant from sensor to sensor because of the repeatability of our products. What I would say is for a given application, if you do a thorough characterization, right at the beginning, if you're not changing the sensitivity or type of sensor that you're using, that characterization should be able to hold after doing it, one time for the circuit that you choose, and then you should be able to use that as a baseline for the subsequent steps of your design process.
Okay, thank you, Ed. Next question here. Looking at the other end of the scale, what is the lowest ranges achievable?
Sure. So on the lower side, and that's an excellent question. Today, as things are, our products are getting smaller, more miniaturized, more modular. The need for lower and lower force ranges is becoming more and more prevalent. So right now, our general recommendation is to try to aim for a contact pressure among somewhere around 1 psi. Our testing has showed that the repeatability and the characteristics of the sensor are most realized at that minimum contact pressure of 1 psi. In terms of forces, given the different shapes and sizes of our sensors, that could translate to something on the order of tens of grams or 50s of grams, and we can also work with you in terms of, depending on the size of your actuator that's going to be loading the sensor, the load concentrators or pucks as we call them internally, that we had mentioned in the presentation. Using those can help to create a smaller contact area and increase that contact pressure for lighter forces to get you to that 1 psi mark. So again, 1 psi is the neighborhood you want to try to be in for a minimum contact pressure. If you need guidance on how to create a situation where you're getting that, given the size and magnitude of your force actuator, we're glad to make some recommendations to help realize that.
Okay, thank you. This next person is asking about trimming the sensor. So they state that they know you can cut it, the FlexiForce sensor, they know you can cut it. The question is, can they trim it? They need a very small sensing area, and they are afraid that if they cut too much of the sensor, it will lose its performance.
Sure. So yes, trimming the leads of the sensor, for example, for our A201 series or our A401 series, that's something we can absolutely do. We can make the leads shorter for you and pin them with our square male pin standard termination, so that you've got a shorter tail length. When it comes to the sensing area, I would proceed with some caution. It is possible. The Now, when you're looking at our sensors, regardless of the shape of it, you're always going to see a similar trend. And what that's going to be is you're going to have the sensing region in the middle of the sensor at the head of the tail. That sensing region is the silver area that the leads connect to, and then you're going to have a black material that's extending beyond the silver. That's the pressure sensitive material that we're printing. What we do is we size that a little bit larger than the silver of the active area to account for registration in our manufacturing process. So when you're considering the active area, you want to consider just the silver that's connected to the leads of the sensor. Now, when it comes to trimming it for a FlexiForce sensor, you can trim into that sensor. The risk you're running is that the perimeter of that sensing region that extends beyond the black pressure sensitive ink at the edges of the sensing region is adhesive that holds the entire sensor together. So by trimming the head of the sensor to make it smaller, oftentimes you're going to trim away adhesive, which could leave the two layers of the sensor apart from each other, or can make the sensor prone to ingress of foreign materials. So if you're doing this as a proof of concept to try to synthesize a specific shape or something like that, what I would recommend for trimming one of our standard sensors would be to take something, for example, like a packaging tape. If you put if you stick a piece of packaging tape to the bottom of the sensor and then to the top of the sensor as well, oversizing the packaging tape relative to the sensor itself, and then go ahead and trim what you need to trim, the packaging tape can essentially act as a new adhesive for the sensor. And then if you're finding yourself with an open edge, you can use a vinyl tape to seal back off the sensor. Now, what you might have after doing this is you could see that there's some preload on the sensor due to the tape, which in that case you could either zero out your electronics to negate that, or you could see that there is now more of a z-axis travel in the sensor because the two layers aren't in much contact with each other. In that case, I would recommend perhaps loading the sensor with some type of constant preload, a loading platform, or if you will, and then tearing that out so that for your measurement of interest, the two layers of the sensor are back in contact with each other. So again, happy to discuss that further. If you want to reach out in an email, one of our applications engineers or myself is glad to provide more guidance.
Okay, thank you so much, Ed. Just a reminder, if you have a question, go ahead and place it in that Q&A window and click submit. And we do have lots of questions, so if we don't get to your question today, we will reach out to you following the webinar. So Ed, the next question, is the force sensor array available?
So force sensor arrays are available. We have other parts of Tekscan which do matrix sensors, which come with full systems and allow you to actually map a pressure gradient across an entire contact area. The FlexiForce sensors are intended to output a discrete force in one contact position, whereas our matrix sensors are intended to, with the systems that they come with, are intended to map an entire pressure gradient across a given contact area. There is an in-between to that, in that our custom sensor solutions, if you're looking for discrete forces in multiple contact positions, if we can create custom FlexiForce sensors with multiple sensing elements in them, and wire the traces or print the traces in an array format. So yes, they are available, and on the FlexiForce side, we can work with you to wire them to wire some standard sensors in an array, so you can prove the concept if needed, and then we can of course work with you to create a custom sensor of an array of discrete sensing elements if that's what your application requires.
Okay, thank you, Ed. Next question here. I purchased a 10 by A301 FlexiForce sensor for specific application. Do I need to characterize each one, or should I characterize only one and suppose the same behavior for the rest of the sensors?
So this is similar to the question that we had talked about before when it comes to characterizing once or previously or multiple times. So hopefully that gave you some foundation to that response. I'll just add or reiterate that for a given sensitivity of a sensor, the output trend will be constant from sensor to sensor. You may see some fluctuations or variations in absolute values, but the output characteristic curves will be, given the circuit you select and your given material interface that you select, will be constant from sensor to sensor in that sensitivity range.
Okay, great, thank you. What circuit parameter can be changed to give the finest resolution of compressive forces of 0 to 5 newtons?
So for 0 to 5 newtons, my recommendation would be to increase the reference voltage. I would probably suggest either using, an op-amp circuit will give you will give you resolution, will give you a constant resolution through that force range, and will give you a linear response through that force range. Depending on if you go with non-inverting or inverting configuration, depending on what your circuit and the budget you're trying to operate in can allow, I would recommend increasing the reference voltage on the order of somewhere between perhaps 2.5 and 5 volts for a reference, and then pulsing that as a square wave as we talked about in the previous questions here. What that'll do is it'll give you more sensitivity in the sensor and allow you to set your gain so that you are at 80%, 80 to 85%, I would recommend, of your maximum circuit output at that 5 Newton mark. The reason I'm recommending a higher reference voltage instead of a low reference voltage and a very high gain is signal to noise ratio. Because you're working in a low force area, you could be prone to either mechanical or electrical noise. So having that higher reference voltage will give you that added sensitivity, and it'll help prevent effects of external noise while maintaining a robust measurement. So increasing reference voltage and pulsing it is what I would recommend for a low force range like that.
Okay, great. Thank you so much. All right, Ed, this attendee is asking, basically they're asking if you can customize. They would like to know if you can create a sensor with a hole through the middle of the sensing area.
Yes, absolutely. So we refer to those as annular sensors. And as part of our custom sensor capabilities, we are absolutely able to do a donut-shaped sensor or a ring-shaped sensor, if you will. We can size the inner diameter as needed, and the outer diameter accordingly. There are some design guidelines in terms of how much space you want from the inner die cut to the sensing region, and then the sensing region to the outer die cut to allow for adhesive and things like that. So please feel free to follow up with us, or we can reach out to you and we can talk about some of those guidelines, and and once you're ready, put you on the path to that type of custom sensor. But yes, it absolutely is possible.
All right, thank you for that answer. We do have time for a couple more questions, Ed, so we're going to go through a few more. Just a reminder to all the attendees, if you'd like to ask a question, go ahead and place it in that window and click submit. If we don't get time to answer your question today, we will reach out to you following the webinar. So next question here, what function does the capacitor serve in the inverting circuit?
Great question. So the capacitor can serve a couple of functions. Mainly, it is essentially with the resistor and the capacitor wired the way it is. It's serving as a filter to filter out noise and to help filter out noise and oscillation. And also it will also set help to set the RC time constant, or the response time of the circuit itself relative to the sensor and the application. So when you're designing your circuit, you want to make sure that the resistor and the capacitor in the feedback loop are sized so that the time constant of your circuit is in order with the sampling rate of whatever you're using to sample your output. So that's that would be the function of the capacitor there. Happy to go over offline considerations and approaches for sizing that appropriately for your application.
Okay, great. Thank you so much. Next question, Ed. Do you have a detailed technical document?
Absolutely. Tekscan prides itself on technical documentation. You'll find that we have a vast library of technical collateral. We have our FlexiForce integration guide. We have electrical and best practices manuals. We have some various ebooks that have been written entailing different design processes and design approaches or measurement approaches. If you refer to our website or take a look at www.tekscan.com/FIR, you'll see some integration resources with technical collateral at that page.
Okay, great. Thank you so much, Ed. So we do have time for maybe one or two more questions. Next question for you, Ed. What is the typical time to get a custom modification on a sensor like A301?
So it will depend on the type of modification. If you're looking with the A301 specifically, I'm not sure if you're saying that you'd like to trim it. I'm not sure how much tail length there is on the A301 specifically to trim, but something like a trimming can be done very quickly, very close to the time it takes us to fill a standard order to begin with. And then if you're looking for a full customization, or if you're looking to just keep the sensing area size of the A301 and change the shape overall, that's entering our custom sensor design process, which can take somewhere between, depending on the complexity and other factors, it could take on the order of 8 to 10 weeks. But I would need to know more specifically about the customization you're looking for to give you a better estimate of the timeline. So please feel free to reach out to discuss that further, and I can give you a more detailed or a little bit more of an accurate answer.
Okay, great. Thank you so much, Ed. So we're almost out of time here. So we're going to wrap the webinar up right now. I just want to say a huge thank you to all of the attendees for asking so many amazing questions. We have a ton of questions that we have not gotten to yet. So again, we will reach out to everybody following the webinar to get everyone's question answered. And I want to say thank you so much to Ed for the great presentation and for taking time to go through all of these questions today. So Ed, thank you.
My pleasure, Katie. And as you said, thank you to all the attendees. The questions were excellent today. There are some excellent questions that we haven't answered yet that, as you had mentioned, that I'm gonna be getting to as soon as possible. And I look forward to hopefully working with all of you on upcoming projects to give you some successful results.
All right, Ed, thank you so much.